G'day. Welcome to Crystal Clear Mathematics, where it is easier than you think. I'm Graham Henderson. I've had a special request in the last day or so from Avis, one of my subscribers, a very new subscriber. And Avis has asked me to try to explain in simple terms the basic principles behind rational functions. Now, this I'm going to try to do. So Avis, there are four basic principles in order to understand rational functions. Principle number one, you must be able to graph polynomials. And I'll demonstrate. If you have a polynomial like x minus 3 times x plus 1 times x, just x, then when we graph this polynomial, there's going to be a 0 at x equals 3. There's going to be 0 at x equals minus 1. And there's going to be 0 when x is 0. And this will give us your basic cubic pattern. But the main thing is to understand the principles of how to find zeros in polynomials. That's principle number one. The second principle is that some number, I'll call it a, divided by 0 is undefined. That is, we cannot divide by 0 legally in our number system. The third principle is the principle of taking limits as x tends to very, very large numbers, in fact tends towards infinity, of expressions like 1 over x, or 1 over x squared, or 1 over x cubed. Now you can see, of course, here we have a fraction, so we are talking about rational functions, ratios or fractions. As the number on the bottom gets bigger and bigger and bigger, provided we've just got a constant on the top or something small on the top, we can make it a 4. This fraction is going to shrink down to 0. So we need to understand that basic principle. Now the fourth basic principle is the principle of division of polynomials. So you must know how to perform a division. And we're going to combine these four concepts to understand how to graph and understand the basic features of a fraction or a rational function. What do I wish to say? These two are going to be very important for us to understand our vertical asymptotes. And these two are going to be very important to understand our horizontal asymptotes. So I'm going to erase this and we'll go through the procedures and understand what's going on. Now the reason I concentrated on talking about polynomials is that the definition of a rational function is this. And you'll see different terminology. You'll see things like y equals fx over gx. Sometimes you'll see px over qx. Sometimes they'll use fx, because really y is a function of x, so they're just making it explicit here. The function is a numerator over a denominator. So you'll see all these different sorts of expressions, but the thing they have in common is that we have a division of two particular functions, and the functions are both polynomials. Now the principles we're going to learn can apply to other functions as well, but we're specifically talking about a polynomial divided by another polynomial. Now let's look at what the implications of this may be. First of all, let's make an example. 2x squared over x minus 3. I think I'm going to switch back to purple because it's a bit more vivid. What was our first principle? Our first principle was understanding that in order to graph a polynomial, we need to find its zeros. The second principle is we can't have a zero in the denominator of a fraction. So here we have a polynomial as a denominator. Now, for all values of x, apart from one particular value, that's not a problem. We can divide by any number we like. We just can't divide by 0. So when x is worth 3 in this case, 3 minus 3 is 0, we have problems. If we made it a bit more complicated, we could have this. Now this would be a more complicated graph to draw, but you can see that we're going to have problems here when x is 3. Another problem when x is worth minus 5, because this would make this expression equal to 0. And another problem when we've got x equals 11. Which means this. Let me interpret it for you. If I try to graph this, now the 2x squared is going to do something else, etc., etc. But if I try and graph this, it is impossible for me to find a value for this expression when x is worth 3. So at x equals 3, on this vertical line there will be no point corresponding for this graph, for this function. And consequently, we draw a dashed line and call this an asymptote. Why does it behave like an asymptote? Well, you can have a value as close as you wish. I can put down x point 0.00005, for example, and substitute it, and I will probably get a very, very large number. So 3.00005 and a very, very large number. And you'll find that we get a typical curve where the function will get as close as you wish to this asymptote, but never actually touch it, and the values will become absolutely huge. They'll tend towards infinity. At minus 5 we have the same problem. We will have a vertical asymptote at x equals minus 5. And at x equals plus 11, I'm sorry I chose that now, let's change that to 8. So at x equals plus 8, 3, 4, 5, 6, 7, 8, we would have another problem here. Now, I'm not saying this is what the graph would look like, but we might have an asymptote here and an asymptote here and an asymptote here and an asymptote over here or something. But the function will be divided up into these panels or these sections. And that's principle number 1, or the result number 1, is that the polynomial on the bottom will give rise to vertical asymptotes. And at this stage, that's all we need to know. 2 principles: find the zeros of the polynomial and realise you can't have those 0 values in the denominator. Let's look at the horizontal asymptotes. Now, I use the expression horizontal asymptotes a little loosely because some of them are not horizontal, and we'll see that. But what's the problem here? Well, now we're looking at the other 2 principles. The principle of limits of 1 over x and 1 over x squared and so on tend towards 0 as x goes to infinity. And the second one is that sometimes we need to carry out divisions. Well, there are three categories we look at here, and the reason that we can be so specific is that we're dealing just with polynomials. If we allowed other kinds of functions, things get a bit nasty and complicated, but polynomials behave in quite a nice way. So let's look at the three cases that we study. Case number one is where I'll use numerator and denominator, where the degree of the numerator is less than the degree of the denominator. What do I mean by that? Well, let's imagine we have something like y equals 2x over x squared plus 1. The degree of the numerator is 1, it's 2x to the power 1. The degree of the denominator is 2. So I have a much more powerful polynomial on the bottom. It's a bit like having a fraction with a very, very large value on the bottom. Now, the problem with this fraction, of course, is it changes value as x changes. To determine what happens with potentially a horizontal asymptote, we must look at what happens to this expression, what happens to y as we take the limit. So here we go. What is the limit of 2x over x squared plus 1 as x tends towards infinity? And we can ask the same question as x tends towards minus infinity. Now I'm going to do both together. Polynomials in fact behave nicely this way, and this is how we go about performing these limits. We divide, we find the highest power in the expression, and here it is, the x squared is the highest power, power of 2, and we divide the numerator and the denominator by x squared. So (2x) on x squared on x squared, and 1 on x squared. We're allowed to do this, dividing top and bottom of a fraction by the same thing. Of course, we can only do this when x is not 0, but as because x is tending towards infinity, it's definitely not going to be 0. So 2x divided by x squared is 2 over x. X squared divided by x squared is 1, and this of course is just 1 over x squared. Now, do you remember what I said as point number 3 at the beginning of this video? The limit of this, something over x, as x tends to infinity, is 0. The limit of 1 is 1, of course, and the limit of this, as x tends towards infinity, 1 over x squared, is also 0. And 0 over 1 plus 0 is 0. So this limit, this function, or the y values if you like, tend towards 0 as x goes towards infinity that way on the graph, and towards minus infinity the other way on the graph. This means that y equals 0 is an asymptote, a horizontal asymptote. It turns out that because there are no zeros for this, there are no vertical asymptotes, and the curve will do something very strange, probably something a bit like that. On horizontal asymptotes, the curve can cross them, just not at the extremities. But I'm going to talk about where to find the graph and such like on another occasion. But at the moment I just want to locate where the asymptotes are. And the curve will tend towards 0 this way, and it will tend towards 0 this way. Okay. what do I wish to say about this? If the degree of the polynomial on the top, in the numerator, is smaller than the one on the bottom, when we perform this little trick of dividing through by the biggest power, which will be on the bottom, we will always get a fraction on the top and it will always become 0. I'll just say that again, just so it makes sense to you. If the biggest power is on the bottom in the denominator, when we divide through by that same biggest power, because the numerator had a smaller power, we're always going to end up with a fraction with x or x squared or x cubed on the bottom in this position. And the limit will always give us a 0. So the rule is, whenever the degree of the numerator is smaller than the degree of the denominator, then you will get y equals 0 is your horizontal asymptote. That is always the case. Let's look at case number 2. Case number 2. If the degree of the numerator equals the degree of the denominator, something happens. Let's have a look at an example. Let's imagine we have 3x squared plus x minus 1 over 2x squared minus 1. Let's imagine we're going to graph this. Here you can see that the degree of this polynomial, it's a quadratic, is 2, and the degree of this one is 2 as well. So the degree of the numerator and denominator are the same. In this particular case, if we take the limit as x goes to infinity, plus or minus infinity, of this expression, what is going to happen? Well, we get this. We find the biggest power of x, which is x squared, and we divide every term by x squared. So we get 3x squared on x squared plus x on x squared minus 1 on x squared. That's those three. Now in the denominator, we get 2x squared on x squared minus 1 on x squared. I'll simplify. The x squareds divide out here and we're left with 3 plus, now here one of these x's will divide out, and here we've just got to leave that as 1 on x squared, and on the bottom the x squareds divide out, so that's what our expression simplifies to. Now when we take the limit as x becomes plus infinity or x becomes minus infinity, remember that third principle. The limit of this fraction and this fraction and this fraction will all become 0 because they're 1 over x or 1 over x squared. So this will be 3 plus 0 minus 0 over 2 minus 0, which is 3 over 2. And that is, by the way, the asymptote will be y equals this limit. And that will become our asymptote. It will be our asymptote. Now I think you can see, without having to go through all of this, that if this power equals this power, and these ones are smaller, that when we divide these out, we're going to be left with 3 over 2, just these leading coefficients. And this is always the case. So when the degree n of the numerator equals the degree of the denominator, the asymptote is y equals the ratio of the coefficients. We can just ignore these other terms. One way to think of it, Avis, is this. As x grows into a massive number, let's say to 1 million, 3 times 1 million squared is huge. Add 1 million to it, not much difference, and subtracting 1, totally insignificant. On the bottom, 2 times a million squared, again, huge. Subtracting 1 won't make much difference at all. So these are the important terms, and the bigger x gets, the more we can disregard these other ones. In essence, that's what all this limit is saying. And then the x squareds would cancel out, and we just have to worry about 3 over 2. So if I had another expression that looked like this, I'll use a black here. So if I had another one, y equals 5x cubed plus 3 over 3x cubed, I would note that these powers are the same, and therefore the horizontal asymptote would be y equals 5 on 3. Because I can ignore this 3 here. When I take the limit, if I actually go through this whole process of taking the limit and dividing by x cubed, I'd have a 3 over x cubed there, and it would become 0 as I took the limit. So this is actually quite a nice little one to analyse as well. The good news with polynomials and with functions is that you're only going to have one horizontal tangent, one horizontal asymptote. Now things get a little bit tricky when we look at case number, that's case number 2, by the way, I should have changed that. When we look at case number 3, when the degree on the top is larger. So let's have a close look at that. Now, this can get very, very complicated, and basically at school, they're only going to give you one where the degree is 1 greater than the denominator. And I'll explain why as we proceed. Let's look at an example. Let's imagine we have 3x squared minus 2x plus 5 over x minus 1. That will do. You can see that here we have a rational function. We have a ratio of 2 polynomials. We have a very simple one in the denominator. Because that has a 0 at x equals 1, you can see that the vertical asymptote is going to be x equals 1. But that's not what we're talking about here. We're talking about the horizontal asymptotes, or at least what are potentially horizontal. And we can see that the degree of the numerator this time is bigger than the degree of the denominator. What problems does that produce for us? Well, if we took our limit the same way as we did the previous 2 times, the limit as x goes to plus or minus infinity, the biggest power of x is here. In fact, let's do this. Let's do it. This would become our asymptote. Y equals the limit as x goes to plus or minus infinity of 3x squared minus 2x plus 5 over x minus 1. And I've written it with a little bit of a gap, so I'm actually going to divide, I'll do it in black. I'm going to divide everything by x squared. Now what does that do? Well, please notice this. Three x squared over x squared is 3. Minus, now an x will divide out here, so we get 2 over x, plus 5 on x squared. And here we've got x over x squared, which is going to be 1 on x. And here we've got minus 1 on x squared. And as per our third initial rule, the limit as something over x or something over x squared as x goes to plus or minus infinity is going to be 0. So this is going to be 3 minus 0 plus 0 over 0 minus 0. And I hope you can instantly see the problem. we're going to have 3 on the top and 0 on the bottom, and we're dividing by 0, which is undefined, so there is no defined horizontal tangent at all. Just can't be done. So, we've got a slight problem. This is not the way to do it because there is no horizontal tangent. That's why this is a little horizontal asymptotes, I'm sorry. But that's why this is a little bit confusing as a heading. I'm going to remove this and we're going to see how our fourth principle helps us to resolve the problem. Now our fourth principle is a principle of division of polynomials. And this is why our definition of these rational functions is so important. If we had other functions here, if I had a polynomial divided by sine x or something like that, I would have serious problems. But we can divide polynomials. I know there's a shortcut, but I'm going to do this the traditional way. Let's perform the division. X into 3x squared goes 3x times, so I put that in the x column. 3x times x is 3x squared. 3x times minus 1 is minus 3x. Let's subtract. That minus that is 0, which is what we hoped for. Minus 2x minus 3x, so that's plus 3x. Minus 2x plus 3x is x. Bring down the 5. X into x goes once. 1 times this is x minus 1. And let's perform this subtraction. X minus x is 0. And plus 5 minus 1. Minus 1 is plus 1. So 5 and 1 is 6. So this is equal to 3x plus 1. That's what we get when we perform the division. So I divide this into this, I get 3x plus 1 plus a remainder of 6. That is still divided by the x minus 1. By performing this division, we see something quite remarkable. Here we have a very recognisable function with this extra bit added on. Now, as I take the limit as x goes to plus or minus infinity, this bit, because it's something over a function of x, will become 0. That's using our third principle. So the limit of this will be 0. So in other words, as x tends towards plus or minus infinity, y will tend towards 3x plus 1. It only differs from that by this little bit that's added on, and that bit shrinks and shrinks and shrinks as we get further and further up towards plus infinity or down towards minus infinity. And this is the secret when we have a big polynomial on the top and a small one on the bottom. We perform the division, we get a polynomial function plus a fraction that becomes increasingly insignificant. And that is our asymptote. Now notice it's not horizontal. This one, I've got such a mess here, I'll just eliminate this. So let's now graph our polynomial. Well, it's not a polynomial, let's graph our function. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. You might have noticed, as I said earlier, our vertical asymptote is at x equals 1. Our horizontal asymptote doesn't exist, but we do have this asymptote. Y equals 3x plus 1. Well, there's plus 1. A gradient of 3 is across 1 and up 3. And across 1 and up 3, and so forth. Or down 3 and back 1. 1, 2, 3, back 1. Down 1, 2, 3, and back 1. So if I did a dotted line here, that is our other asymptote. Now, the one thing I didn't add is there are two things I haven't added. One is, in trying to graph this, knowing where the function cuts the x and y axes helps. So in other words, looking for the x and y intercepts are important. So let's do that. I'll change to black. If we let x equals 0, now what equation is x equals 0? It's this line, isn't it? So we're going to find whether the curve cuts the y-axis or the y-intercept. When x is 0, what do we get? We get 0, 0, 5, and 0 and minus 1. So when x is 0, we're going to get 5 over negative 1 when x is worth 0. Now if I put that together, I get minus 5. So y is going to be worth minus 5 when x is 0. 0, negative 5. So the curve goes through that point. Let's remember that. What about y equals 0? Well, that's a bit more difficult. For y to equal 0, that means this equals 0, and the only way this equals 0 is if the top is 0. I really don't care what the bottom's worth, but I do want the top to be 0, and I've got to find zeros of this quadratic. Now, it's not instantly factorisable, so you might try to work out the discriminant, b squared minus 4ac, to see whether it's factorisable. Let's do this. B squared is going to be minus 2 squared. A times c is 3 5s are 15. I'm scribbling this a little bit. Minus 2 squared is 4. 4 15s are 60. This is negative. Right, it's less than 0, therefore no roots. So there are no zeros. So in other words, the curve does not cut the horizontal axis at all. Now, how does that help us graph the function? Well, if the function goes through this point and can't cross this asymptote and can't cross that asymptote, then I think you can see it probably does something a bit like this. The other principle of these functions is that because they're a function, I can't have any graph here because the vertical line would cut it twice, the function twice, if there was a bit here and a bit here. They tend to alternate, a bit like a chessboard. So diagonally across here we'll have a corresponding part of the function. And that's how this would be graphed. Now, of course, you'd need to substitute some points if you wanted to get some exact positions, but that's the principle. The principle of finding which parts to fill in are basically by substitution, and particularly finding the x and y intercepts. I think that's all I wanted to say in this fairly lengthy video. If you've got further questions, then please send me a message. There's one tiny last principle that I want to share, and it's not commonly talked about, but I think it needs to be shared. So I'll just remove this and share the one last concept or idea, and hopefully this will be of use to you. I'm going to talk about how to graph this particular function. It's a very simple one. Y equals 4 over x minus 2. The first thing to notice is it is in fact a rational function. We have a very simple polynomial in the denominator, and it does have a 0 when x is worth 2. 2 minus 2 makes a 0. So our vertical asymptote is where x equals 2. Let's just draw this very quickly. 1, 2. So we've got an asymptote here. Our horizontal asymptote, because this, the numerator, is a lesser degree than this, that's 4x to the 0 if you like, it's just a constant. And we learnt as the first of those three things that we looked at, that when the numerator has a degree smaller than the denominator, we have a horizontal asymptote at y equals 0. Now you should recognise this as your basic hyperbola. The 4 means that we're looking for factors. If I rearrange this, y times x minus 2 equals 4. We're looking for factors that multiply to make 4. By the way, another way to think of asymptotes is if y equals 0, 0 times something can never equal 4. And if x equals 2, to make that 0, 0 times that can't equal 4. So in other words, having either of these factors equal to 0 gives us an asymptote. That's another way of looking at asymptotes. But we're looking for pairs of numbers that make 4. And y equals 2 and x equals 4, because 4 minus 2 will be 2. 2 times 2 is 4. So this distance here will be 2, and this distance here will be 2, and we'll get a section of the graph here. And if I come back 2 and down 2, so that this distance is 2 and this distance is 2, my other part of the graph will do this. Similarly, up 1 and across 4 will do it. Up 4 and across 1, and the same back here. Back 4 and down 1, or back 1 and down 4 will give me that factor, the factor of 4 here, or the multiple of 4. The principle I wanted to explain to you as the last little step is this. What happens if there is a common factor? Now we normally assume there isn't one. But what if I had x plus 3, for example, multiplying the top and the bottom? Well, you can see that x plus 3 over x plus 3 is 1 for every value of x, except for 1. But for every value of x is equal to 1, which means we're multiplying by 1, it makes no difference to the graph whatsoever, except that by doing this, we're now saying that when x is worth minus 3, we would get a 0 over 0, which is undefined. So suddenly, by creating this extra factor, we're saying that when x is worth minus 3, we don't get an asymptote because we have the same factor on the top. We just get 0 over 0, and it means that at minus 3, there is a gap in the graph where there is no value. But right up to the points either side of it, it behaves exactly the same way it always did. So you can poke holes in graphs. If I wanted a hole up here at there's 3, 4, 5, I would simply put x minus 5 over x minus 5, and that would poke a hole in my graph there. So I just wanted to explain this, just so that if you see one in a test like this, you'll get presented with something like this. Here would be a classic. There you go. You may not recognise it as that, but when you factorise it, you would get x minus 2 over x minus 2 times x plus 2. Once you factorise the denominator, and you notice we have this same factor on the top and the bottom. So this is really the graph of 1 over x plus 2 multiplied by x minus 2 over x minus 2. That's what it is, but that's the actual graph. So I graph 1 over x plus 2, asymptotes at minus 2, horizontal asymptote at 0. So the graph is doing this sort of thing, and I've got a gap where x is worth 2. Sorry, I really scribbled that, didn't I? But I hope you've got the idea. That's the last little principle. What happens when you have a factor in the numerator and the denominator? So I think we've covered all bases. There are 4 basic principles. The principle that you need to be able to factorise polynomials and know about their zeros. The principle you cannot have zeros in the denominator. You cannot divide by 0, and that's what gives us our vertical asymptotes. The principle of taking limits of functions when they're of the form 1 over some power of x, and those limits are always 0, and the principle of division. And putting those last two together helps us find the horizontal or the oblique asymptotes. And this last little principle is simply to see what happens when we have this little pattern. If you've been struggling with rational functions, I hope this has been a help. I realise in one video it's impossible to cover all the bases. I know it's been a lengthy video, but if you have questions or comments to make, please put them under the video. If you like the video, please of course click the like button. I always appreciate that. And if this is your first visit to Crystal Clear Mathematics and you like what you see and you would like to see more, then please subscribe so you can find out as each video is posted. Thank you very much for watching, and I particularly want to thank Avis for asking the question. Thank you very much. I hope this has helped.